Engineering a building starts with static lines on a blueprint, but the reality of operating it is continuous and chaotic. Shadows sweep across facades, occupancy fluctuates, and weather changes by the minute. Sizing HVAC equipment is a discrete mathematical task. Engineers calculate the absolute worst-case scenario, the peak thermal load, and select equipment capable of handling that single extreme. A system only runs at that maximum design capacity for a few hours out of the 8,760 hours in a standard year. The primary challenge of energy modeling lies in the rest of the year. The vast majority of an HVAC system's life cycle is spent operating at part load, constantly adjusting its output to match partial thermal demands. Energy modeling exists to navigate this part load reality. It is an economic analysis tool used to determine which design option offers the lowest total life cycle cost, rather than just identifying the cheapest initial equipment. To calculate this, models must track two core dynamic variables: fluctuating outdoor weather conditions and varying internal heat gains from people, lighting, and electronics. They must also differentiate between the energy source, the electricity or gas delivered to the building meter, and the energy resource, which is the raw coal or gas extracted from the earth to generate it. Predicting how much energy a building consumes requires matching the calculation method to the building's complexity. This means navigating three distinct tiers of resolution: degree days, the bin method, and hourly simulation. Selecting the right tier is increasingly mandatory. Many building codes now require detailed energy analysis to prove compliance with performance goals before a municipality will issue a permit. Using an inadequate tier of modeling produces a massive discrepancy between a design's theoretical goals and the actual energy bills the owner pays. The first and simplest tier of modeling relies on a foundational metric, the balance point temperature. This animated diagram illustrates the balance point, where internal heat gains perfectly offset envelope heat losses escaping through walls and roof. We calculate this equilibrium directly. The balance point equals the indoor set point minus total internal gains divided by the building's loss coefficient. The mechanical heating system only needs to engage when the outdoor temperature drops strictly below this calculated balance point. For decades, the industry standard was to assume a universal balance point of 65 degrees Fahrenheit, using it as the fixed base for calculating seasonal heating degree days. Modern buildings feature highly insulated envelopes and house dense heat-generating electronics. Their true balance points are often much lower than 65 degrees, making the historical base highly inaccurate. The variable base degree day method corrects this error. It counts degree days relative to the building's actual calculated balance point, rather than relying on an arbitrary historical average. Even with an accurate baseline, the degree day method relies on a rigid assumption that the efficiency of the heating system remains entirely constant regardless of the thermal load. Because of this assumption, degree day calculations are reliable only for small, envelope-dominated structures running conventional furnaces or boilers with steady efficiency curves. While correcting the balance point improves accuracy, any steady-state method falls apart when applied to modern systems where operating efficiency is a moving target. When HVAC equipment efficiency fluctuates based on the outdoor temperature, the single-measured degree day approach mathematically fails. This chart maps the performance of an air source heat pump. Notice the intersection exactly at the balance point, where heat loss meets capacity. As temperature drops, moving left along the x-axis, a critical gap widens. Heat loss climbs linearly, while capacity steadily plummets. Degree days cannot reconcile these two conflicting variables. Averaging the entire winter season into a single multiplier erases the extremes, where the equipment operates least efficiently. The solution is the bin method. Instead of a single seasonal average, this approach groups annual weather data into specific 5-degree increments, or bins. Engineers calculate the specific equipment capacity, part load efficiency, and required operating time separately for every single temperature bin.
Segmenting the data this way allows the model to accurately trigger and account for expensive, inefficient supplemental electric heating only during the exact bins where the primary heat pump capacity is exceeded. During the summer months, mean coincident wet bulb data is tied to these dry bulb bins, enabling precise calculations of latent cooling loads driven by humidity and infiltration. The modified bin method refines this further by splitting the bins into different times of day, capturing shifting solar gains and varying occupancy schedules. The bin method elegantly handles variable efficiency, but it still calculates loads in isolation. It lacks the capacity to model the complex feedback loops between interconnected systems inside a large commercial facility. Large-scale commercial building simulation requires tracking 3 interacting layers of thermal transfer: the space load, the secondary distribution systems, and the primary central plants. This diagram outlines the sequential modeling strategy used in many traditional building energy programs. Notice the solid black arrows showing data passing in a strict one-way sequence from the load model to the system model and finally to the plant model. This schematic details a secondary system. Specifically, these are the variable air volume terminal units and reheat coils that distribute the conditioned air to the actual building zones. In a sequential model, all individual space loads are pre-calculated and fixed for every hour of the year before the secondary system or primary plant models ever run. The structure of this calculation sequence creates a severe blind spot. If the primary plant, calculated last in the chain, becomes overloaded and cannot meet the demands passed to it, the model hits a dead end. In reality, if a chiller plant maxes out, the chilled water temperature rises, coil capacity drops, and the physical room temperatures drift upward until the load matches the available capacity. The sequential model cannot simulate this room temperature drift. Because the space loads were pre-calculated and fixed in step 1, the program can only log the deficit and report an unmet load. This decoupling prevents engineers from analyzing how varying supply water temperatures from an overloaded plant directly degrade the capacity of secondary coils. Furthermore, these sequential programs rely on rigidly predefined system templates. Modifying a system architecture often requires altering and recompiling the underlying source code. By decoupling the load from the equipment, sequential models ignore the basic physics of thermal interaction during moments of peak system stress. Modern energy simulation engines discard the sequential sequence entirely. They solve the equations for the load, the secondary systems, and the primary plant simultaneously at every single time step. This illustrates the shift. On the left, the linear, decoupled strategy. On the right, a simultaneous network where space loads and central plants are solved together. A central plant shortage immediately cascades down the network, forcing simulated room temperatures to readjust. Achieving this level of accuracy requires intense computational power and a high degree of user expertise to configure the precise, sub-hourly time steps. These simulations can be structured as forward modeling, which builds a thermodynamic profile from the physical geometry of a blueprint, or data-driven modeling, which uses statistical analysis of actual performance data from an existing structure. Regardless of the engine, building models are designed to compare the economic viability of design alternatives. The vast number of unknown human variables in a real building means these models should not be used to predict absolute future utility bills. The choice of model dictates the reliability of the analysis. For small structures with constant efficiency equipment, the variable-based degree day method provides a fast, accurate baseline. When equipment efficiency shifts with the outdoor temperature, the bin method maps those nonlinear variations across the spectrum of annual weather data. And for complex commercial facilities full of interacting feedback loops, simultaneous hourly simulation engines provide the necessary dynamic resolution. True energy prediction is an exercise in matching the engineering resolution to the complexity of the variables. When the modeling tier aligns with the building's thermodynamics, the resulting economic analysis moves from an educated guess to an engineered certainty.